Yeah, welcome to this session star 4, where we will have two other state-of-the-art reports. They last about 50 minutes. My name is Bernhard Preim. I'm from the University of Magdeburg. It's a pleasure for me to chair this session. The first state-of-the-art report is entitled A Survey on Visualization for Musical Data. So it is about musicology, a part of digital humanities. The team of authors is primarily from the University of Leipzig and the University of Southern Denmark in Odense. Richard Jakob Kusnick is the speaker. So it's a pleasure for me to introduce him to you. He is personally involved in this type of research and was very active also in the Museum for Music. So he has a strong background in this, and we can be very excited about his talk. The stage is yours, Jakob.
Hello, I'm Jakob Kusnick and want to give you some insights into the state-of-the-art visualizations for different kinds of musical data. First of all, let's talk about the domains. The term musicology comes from the Greek words for music and a domain of study. Hence, musicology is a domain dealing with all kinds of music-related analysis and research. Although it is mainly classified as a humanistic domain, it also has some parts of scientific studies, especially in the sociological and neurological fields. Like the name, the field has a century-long history because of the blooming musical culture and since ancient times. Let's fast forward to the digital humanities. This field of study is the advancement of traditional humanities like musicology, history, or literature by computational power. In the traditional humanities, the digital humanities is sometimes seen as a kind of replacement of their traditional methods. Actually, it is rather a movement to support traditional approaches and allow for shared work, accessibility, and handling of quantities of data in short time. Besides this support of traditional approaches, it also enables humanists new research questions, sometimes not even imaginable in traditional approaches. Visualization is just one of the major computational approaches because of its strength to enable visual pattern recognition. Besides musicology, many research domains already adopted digital humanity approaches and showed their values as well as usefulness. Nevertheless, and due to the feeling of the digital humanities wanting to replace traditional research, the musicology itself is still only marginally influenced by the digital humanities. The projects we included in the survey are from the 2 last decades and showed great potential for the field by crossing both domains. This state-of-the-art report gives an overview over these projects, why they are relevant for the musicology as well for the visualization community, makes typical issues aware, and lastly adds future challenges to advance the field. Musicologists work on different types of entities. We classified projects by their type of data used and then by their task addressed. So let's us have a look at our classification of musical data. Next to some examples on the slide, we can see a bar chart presenting the distribution of used visualizations for the different kinds of data. We classified 4 main types of data. The first one deals with the results of music. We call it the musical works. Musical works are divided into musical scores, the traditional documentation of music, and musical sound as a result of performing musical works on instruments or by voice. The second category deals with collections of multiple of these musical works. This may be a playlist of songs, an album of a band, or whole genre. Next are the persons involved in musical culture. This may be a composer, instrument player, teacher, or student, but also other persons connected to the music culture and industry like instrument manufacturers or publishers. Last but not least, we will talk about the objects used to create music itself, the musical instruments. Before we get more insight into the projects for these entities, we have to talk about the frame of this work. On the slide, we can see the different research domains which we included in the survey, as well the amount of projects published in each. Most of the projects are from the visualization domain itself, but there are also specialized conferences or journals aiming for new approaches for human-computer interaction or music information retrieval. We want to highlight that we decided to exclude works using input to generate music or with very simple and static graphs like scatterplots of song similarities, for example. After this long introduction, let's have a look at some pictures. The most basic and known visualization of musical works is a note sheet. Here we can see a note sheet of Beethoven's Fürliese, consisting of 2 tracks with sequences of notes instructing a skilled musician in how to interpret the song. While this is a state-of-the-art used in documenting music, it is very traditional and only borderline on the visualization part. The image on the right shows the same song represented by Wattenberg's arc diagrams, while here we lose the information needed to replay a song. We get clearer insight into structural features of the song. Arcs are connecting recurring patterns with the line strengths being the number of notes, so the length of the recurring pattern. In general, we found 3 important tasks for the musical scores visualizations: giving overview of a whole song, enabling structural analysis, and further helping in instrument performance analysis. The third example uses the very common approach of different heights for different pitches and a sequential order of notes throughout the time. This approach is called a piano roll view and also adds color for keys and harmonic relations between tones. On the right side, we see a similar approach, where higher pitches than the ground level major C create red and yellow lines, and lower pitches in blue or green shades pointing downwards. Why is this type of data relevant for the visualization community? First of all, the representation of notes is a unique feature of music and not much researched on. Although, through the traditional music sheet notation, a kind of pre-digital visualization has been established, which may be interesting to be analyzed. We learned in general that visualization and musical work representations have a lot in common. Both use visual features to represent information and excel in teaching or presenting. On the other side, bringing more visualizations principles to the music scores benefits the musicology. While a note sheet is easy to use for a skilled musician, especially beginners and domain-extern people struggle with this rather unintuitive design. Visualization in general has shown to be able to give a quick and easy access to complex data. A third benefit lies in the support of analyzing music. As seen in the arc diagram example, structural features of musical works can easily be highlighted, giving faster insight into such patterns and features. The next kind of data is about musical sounds. In contrast to the prior one, the focus lies on sound features like pitch, loudness, tempo, and timing. Sources for such data are either live recordings or audio files. Typical tasks for this kind of data are the analysis of performance, of emotion, or similarities between songs or performances. Here we have 2 examples. Both are trying to visualize the flow and emotions of a song either by a piano roll-inspired layout of cycles with different sizes, heights, or colors, or dance performed by animated figures. While this animation of avatars allows for mapping of the mood or emotion of a song to human-like movement, the other example maps the sound characteristica to complex shapes. The next 2 projects are different visualizations using graphs and score visualizations. And trying to give feedback to a musician's performance either by audio features or with additional audience votes. The example on the right side uses also an island-like metaphor and allows for a similarity check between different resulting islands. Again, the similarity between visualization and music could be found in these projects. Both try to communicate information. Especially interesting is the visualization's ability to map audio features to visual ones, helping or even enabling hearing impaired people to get access to music or sound in general. For musicologists, the visual representation of learning sessions is of high value and can give a student feedback in how a performance went and what needs to be improved. Also, it allows to find and define fingerprint-like styles for a musician, helping in analyzing the person. Next, with the help of visualizations, the user can get an enhanced listening experience through an active role in interacting with the sound. Lastly, the visualization of musical sounds helps in comparing different interpretations of the same musical piece or song. After we just had a look at a single musical piece of performance or the comparison between two, the next chapter deals with the visualization of whole collections of music. Examples of collections are musical playlists, a band's album, archives of music, or other kinds of sets of musical pieces. The projects we found for this kind of data were specialized in giving users means for explorative analysis, access to listening statistics and their analysis, as well as music alignment. On the left side, for example, we see a hierarchical and zoomable map of the variety of musical genres. We define the relevance for the visualization community as getting access to non-expert users and their interest in casual and intuitive visualization systems for a large variety of data. Similar to this, musicologists can be interested in these visualizations too, for having examples of how to spark interest in less experienced or casual users and conveying complex data and metrics to them. Although we just talked about only casual sets of music and non-expert users, also more complex systems addressed to musicologists and their research interests are possible, especially motivated through a growing interest in music alignment visualizations, helping in analyzing recurring sound patterns. Here on the right side, we see the very popular islands of genres, which maps musical works by their characteristics. The last two kinds of data deal with the producing elements of music. The group of musicians consists of all people associated to music, often interprets, but also composers, instrument makers, teachers, or publishers. Data here consists mainly of metadata of these persons, like names, temporal data of life and work, professions, related institutions, relations to other musicians, music pieces, or instruments. This set of data is often tainted by uncertainties, on which we'll give more insight later on, but should always be considered when working on musicological data. Again, we could find mainly analysis tasks for which visualization systems have been deployed. These include explorative analysis, social network analysis, and again, similarity analysis. Although we name it as relevance for the visualization community, it may whether be called as challenges for the visualization community. As noted before, biographical metadata of persons in musicology, especially historic data, is heavily uncertain and inhomogeneous. The relevance for the VIS is that here relies a lot of improvement to use the visualizationist skills in working with incomplete, imprecise and inhomogeneous data, and both communicate these flaws in the visualizations as well as deploying strategies in overcoming distortion caused by this. As for the musicology, we found the most common visualizations for this type of as being network graphs of interprets or bands. Mostly they link these persons or groups and use size to communicate a kind of importance. By nature, this gives a good insight into heavily connected and famous persons, while the less connected or less famous person are lacking. An influence of visualization techniques can help in developing new approaches on the data. Our last kind of data are the objects used to produce music. Mainly, projects in this category give insight into structural analysis of instruments or allow for an analysis of how they work. For example, here on the right is an approach to give an insight into the instrument when it comes to the interpretation of electronic music. Here, the abstract settings and effects of buttons or knobs are mapped to the three-dimensional objects which are transformed by them. The structural analysis is similar to non-musicological domains, as they use imaging techniques known from the medical or industrial domain. While these domains are advanced in knowledge of these techniques like computed tomography, the musicology offers a broader set of materials causing lots of issues normally not encountered. They are rather unusual combinations of materials like wood and metal are causing different kinds of artifacts for which we need new approaches and heuristics. This is completed by new research questions untouched by the visualization community, like evaluation of long-term effects of climate on materials, like seen in the topmost example with deformations of an instrument through a longer time span. As for the musicology, these projects are especially important as they offer non-destructive analysis, shared work with historical and fragile unique objects. This also allows for educational purposes, as many types of instruments require view insight to show how they work. Hence, animation of virtually sliced up instruments make it easily to grasp how instruments work. During our work as visualizationists in the musicology, as well as during studying the 129 works included in our survey, we encountered a vast amount of issues with the data, which we will present under the flag of inconsistencies. We classify these as vastness, imprecision, incompleteness, and inhomogeneity. While these issues are well known in the visualization domain, a lot of encountered works seem to be neglecting the dealing with such inconsistencies. We want to include a brief insight into these issues to highlight the importance to deal with them. In general, more data is always welcome, as it gives a more complete insight into the represented real-world aspects. An issue encountered when mundane systems are deployed for vast data are, for example, overlapping, visual overload, and in general size issues. Vastness of data, when not handled correctly, lead to a loss in usefulness for visualizations. This is only increased by complex and multimodal data. These mundane systems could often be improved through meanings of filtering, clustering, and a combination of focus and context, or specialized techniques like edge bundling for network graphs. Imprecision is an issue encountered on a broad set of data. Especially working with audio data can lead to issues with imprecision. This is caused by audio signal being prone to noise. Either background noises or artifacts like white noise for sound or radiations from metals in imaging techniques are common. While we suspect the projects dealing with musical sound having given this issue some thoughts, we hardly could find information of if and how the authors dealt with this issue in their papers. And while the dealing with these imprecisions are of high relevance for the analysis of results, it would also benefit the field to share the gathered knowledge of how to work with these issues. An example of communicating such imprecisions and adapting the visualizations to reduce the cost distortion has been shown by Jänicke et al.'s musicians profiling. The image on the right side shows living spans of musicians as well as shapes indicating the precision of a given date in historical documents. A bar, for example, indicates a precise date, a circle, a span of a round, and a triangle as before or after, pointing in the direction. Further, we encountered incompleteness. This is mainly due to the century-old history of musicology and the work with historical sources. For an information corpus, it is most unusual to be complete, starting with the missing of entries over unreadable documents to missing data through radiation artifacts. In some cases, missing information may be reconstructed or at least hypothetically regenerated as shown in a pipeline by one of our own projects below. Usually, this is not possible and hence the visualizations need to address and communicate this issue, making it clear that data is missing rather than showing a real word pattern. Also caused by the historical nature on the field, a lot of inhomogeneity is to be expected. This is further driven by qualitative research on the field, leading to single entities being deeply researched on, for example, very famous musicians, while thousands of possible similar entities are hardly looked upon. With the exception of these often research entities, research on a specific entity may vary quite a lot depending on the source. Stating of the source and inclusions of possible multiple and contradictory data would be important for an unbiased and complete view on these entities. To make matters worse, data is often given in weak or even non-standardized form. Terms and definitions are not set in musicology and change their meaning with their temporal context, making it harder to communicate findings to non-expert persons. Here, for example, we see the development of lutes and guitar-like instruments and their changing names throughout the times. Another example are the vague names for music genres. We concluded our survey with a list of future challenges we give to the visualization and musicology communities to improve the field and advance the state of the art. First of all, we want to highlight the importance of the interdisciplinary collaboration between both domains. We learned that projects adapting this collaboration showed great potential and use for the field. Next challenge, building upon the musical score and musical collection projects, is adapting of the digital humanities approach of distant reading to musical collections. While we found distant reading approaches for the different data type, we found such views on score collections as something mostly missing and bearing high value for the researchers of both fields. Likely for the instruments, we would challenge our colleagues to work on metadata visualizations for the instruments. Most projects deal with work on scans of the instruments, which are of course of high value. Nevertheless, a whole branch of musicology, the organology, is focused on detailed research of instruments, and work supporting them in these tasks are missing. Also, with the development of scan and print techniques, the reconstruction and reproducing of historical instruments for research, teaching, or presentation purposes needs to be covered. Another facet less approached is the theoretical work of musicologists, also caused by the long tradition of musicological work. Daily workflows are very analog and manual. A get-together between visualizationists and musicologists could offer great support in enhancing of daily workflows and how to work with data and upcoming research questions. Next, we gave insight into typical issues while working with historical data. These need further work on. On the other hand, to find sturdy ways to deal with them, as well as more awareness for communicating them in published works. Last but not least, we found musicology to be a field of high fragmentation. It was almost too easy to classify works into these different data types. Projects giving a comprehensible and complete insight into musicology may offer a whole new world of musicological research not met by the traditional field. And with this promising outlook, I will lead over to gratitude for your attention.
Yeah, thanks a lot, Jakob, for this great presentation for a topic that is not so often discussed at EuroVis, so that really adds to the diversity of the topics that we have at EuroVis. Thanks a lot for this. In the chat, I see one question from Tim Geritz from University of Münster. First, he comments, this is such an interesting topic. And then the question comes, as someone who makes music myself, the most visualization I came across is in the production of music in digital audio workstations, where plugins such as filters alter sounds. These use a lot of different approaches and metaphors to allow users to understand how the parameters will change the music. Is that any work you have encountered looks at, or have you looked into such visualizations yourself? That was a quite long question.
Thanks for the question. Of course, we saw these visualizations many times during our research, and but we decided to exclude them for this survey. So we explicitly excluded production software.
Mm-hmm. Okay, yeah, that makes sense. Mm-hmm.
Yeah, because it's not this interactive visualization we searched for.
Mm. Yeah. There's a second question, meanwhile, from Nuska Smith, University of Bergen. Hello, Nuska. Are you aware of any work exploring the visual style of band logos and album covers in relation to the genre of music?
If I remember correctly, we encountered one or two publications considering this. So something like visual collages of album covers. I don't know, maybe Richard or Christofer, do you remember other works?
I think I remember something, but the first thing that came to mind is always when talking about genres. From our own experience in musicology, we always are very cautious when the term genre falls, because sometimes genres are very hard to classify, and the musicologists we work with are always not so happy if we want to talk about genres, because they say from the field itself, it's more or less controversial which genres are even available. So we have included, I think, 2 works in the survey with deal mainly with the distribution of genres, or the map of music. Music map is one of them. But I don't think we have any works that go into band logos or album covers included.
I think there were one work that focused on covers but not on a comparison site, just for the presentation.
Yeah.
But I think we excluded it because it wasn't really fitting the scope of the survey.
Yeah. Yeah, there's a further question from Silvia Miksch, Technical University of Vienna. Thanks for the inspiring work and nice talk. The question is, can you elaborate about specific visual representation and metaphors for musicology? Are there some more prominent that in our fields? Specific visual representation and metaphors for musicology.
Yeah, hard to say. I mean, we included overview table and bar chart about typical used visualization types for this for the different kinds of data concerning musicology. I don't know.
One thing that was really prominent was the piano overviews, which are basically timelines, and a lot of musical maps. So this island of music metaphor was used a lot. And network graphs for biographic information.
Okay, thanks. Yeah, here's a further question from Adri Chi. Thank you for your comprehensive presentation. Did you save the uncertain dates in your database?
Yeah, in our used database or created databases, we save these uncertainties and encode them or try to encode them in our database as well in the visualizations.
So this is a question more at our own work, and in cooperation with our musicologists, we've tried to dissolve these uncertainties. So we have something like the birth of a person is known to be before the 17th century, and depending on the century itself, we can say that uncertain dates may be a span of 25 years, or maybe even 2 years if it is the 20th century, which offers a much higher level of confidence with such dissolvences.
Yeah, thanks. A further question from Tim Geritz, University of Münster. Do you see clear connections between visualization approaches that have been used on non-musical data that could be applied to musical data, but have just not been used so far? And do you see a reason for that, if this is the case?
Very good question. That there's nothing that just spontaneously comes to mind for me.
Yeah, same here.
But I would be surprised if there isn't anything that could be adapted and put to use in the musicological domain.
Yeah. I mean, the scientific visualizations that visualize 3D spatial data, vector data, tensor data, that probably makes no sense for musicology. Yeah. But perhaps other information visualization techniques, theme rivers or whatever. Okay, yeah, let me have a look in the chat. Adri Chi again has a question. In case of the uncertain dates visualization, how did you save the uncertain dates on disk?
Yeah,
Jakob?
Yeah, as you said already, we saved some possible time spans around uncertain dates, for example, and this is also depending on the century, because in earlier centuries, it is more likely to be uncertain for a date. So these possible time spans are just the whole century, and in later years, maybe a few years.
Thanks. Nuska Smith, University of Bergen, has another question. One of my students is also a musician and wonders if there is a way to empower people without instrument skills to make music on their own. Could interactive visualization play a role here, in your opinion? For example, using virtual instruments?
Definitely.
Many of the encountered works were focusing on some intuitive way or immersive way to touch the user. So many of them displayed virtual instrument or try to visualize them in an immersive way. So, for example, Guitar Hero or something like this.
We have multiple games included that try especially this, give users without instrument skills access to generating music on their own, or to reinterpret given music, like, for example, Guitar Hero.
Yeah, thanks. Another question from Matthias Miller. Really great work and nice talk. The question is, I was wondering whether you encountered any techniques that support visual analysis of melodic motifs based on musical score data like MIDI or music XML.
Exactly. MIDI or music XML were some of the data basis of some of the musical structure analysis visualizations, I think, when it comes to score visualization or musical sound visualization.
Yeah. Okay. Yeah, there is no further question in the chat. Let me ask a question. If you would think about this whole topic from a user-centered point of view, then you would primarily ask for what are different user groups. I think you mentioned sometimes experts and non-experts. That certainly makes sense as a first distinction. Could you further classify the user groups for which this could be essential?
On a more detailed level, we have something like researchers who are, I think, interested in all 4 of the data categories. We have non-research persons that are, for example, instrument players or someone who performs music, who creates music. We have also contact to people from the craftsmanship domain, so people who build instruments or repair them, which are especially interested, of course, in the last chapter, so the visualization of instruments. We have seen some works of violins and their densities, which are conducted by people who are interested in preserving these objects. Jakob, any additions you have in mind right now?
Not really.
So there are a lot of different groups, but I don't think we have them classified in the survey anyway.
Yeah, you cannot use all possible taxonomies. Yeah, that is perfectly valid. Yeah, that just came to my mind. And the follow-up question would be, if I think of other application areas like cultural heritage or biology or medicine, which I know best, typically what helps the users there most are whole systems that provide some guidance, some workflow, starting with handling some quality problems first, processing the data, and then a lot of flexibility added. Did you also came across such whole systems where visualization is only part of it, or did you encounter more individual techniques?
Yeah, I would say we encountered mostly specialized or tailored systems that are put to specific use cases and less tools that try to give comprehensive access to the data itself. Which I would, I think the reason is that the state of the art for visualization in musicology is quite
in its infancy.
Yeah, it's rather basic, and there is a lot that can be built upon the already done work. But such comprehensive works are, I would say, not available at the moment.
Yeah, that's plausible. Yeah, thanks. Meanwhile, there are two further questions in the chat, again from Tim Gieritz. Did your research make you listen or make more music?
Of course, listening. So during our research, we encountered some intuitive and nice and exploring visualizations, for example, for genres. And we explored some new genres for us. And so, of course, new music.
We spent some time looking through the landscape of genres and just clicked on audio examples. And it was informative and funny both.
Yeah, that's nice. That's how research should be. There's a further question from Matthias Miller. Okay, nice. I was wondering to what extent interactivity in analysis approaches is relevant in the visualizations you have investigated. Wattenberg's arc diagrams are rather static, for instance.
Yes. The arc diagrams are indeed something very static, which we wouldn't have included in the survey if they hadn't such a good possibility of visualizing the structure of the pieces.
Yeah.
So the visualization itself, even without the interactive part, gives a high level of usability or access to the structural analysis of the data.
Yeah. Yeah, so we focused on interactive visualization, but mixed some more static visualizations into it if they had a unique feature to show.
Yeah, that makes sense. I mean, your survey is entitled A Survey on Visualization for Musical Data, so that perfectly fits, yeah. Okay. Yeah, I see no further questions, and I also have no important questions myself, even if there is some time left. There's one final from Matthias Müller. What's your favorite visualization technique? Yeah, that should be answered, of course.
That's hard to answer. Of course, there were a lot of great visualizations, but a single technique.
So I think I like the piano wall views for hearing impaired people. I found it quite nice to give access to people that are hearing impaired. But just an example from the top of my head. So
yeah, in general, timelines. So you can think of the piano roll. Yeah, like it's similar to a timeline. Yeah, and you can also draw all musical logical history on your timeline and so on. Yeah.
That makes sense. The timeline is really a familiar visualization to many people, even outside the experts. Yeah, that the x-axis denotes time. That is something people are really familiar with. Yeah, that makes sense. Yeah, with this, I would close the discussion. Thank you a lot for the presentation and also for handling all these questions. It was nice that you teamed up to answer them. Yeah, and best wishes for your further work on this interesting topic.
Thank you.
Thank you.
Yeah, it's a great pleasure for me to introduce the second speaker, the second state-of-the-art report entitled Uncertainty-Aware Visualization in Medical Imaging Survey. The authors are Christina Gillmann, Dorothee Saur, Thomas Wischgoll, and Gerik Scheuermann from Leipzig University Medical Center, and Wright State University in the US. Uncertainty visualization is a great topic since at least 15 years, almost 20 years. In visualization in many areas. You all know that a weather report is not perfectly reliable, or that the further progress of a hurricane or how the climate change. So these are areas where we know that uncertainty has to be handled somehow. But medicine has some unique characteristics. The data is weak and noisy full of artifacts on the one hand, and on the other hand, medical diagnosis and treatment, of course, is a serious issue. So therefore, there was a lot of research carried out also on uncertainty in medical visualization. Christina Gillmann contributed herself a lot to this. That was the core of her own PhD topic. So she was in an excellent position to write and team up with others to create this survey on uncertainty-aware medical visualization. And with this, I want to let the stage to you, Christina, please.
Hey everyone, and welcome to my talk on uncertainty-aware visualization in medical imaging, a survey. This is a joint collaboration between Leipzig University and Wright State University. My name is Christina Gillmann, and I'm going to guide you through this talk. I first want to start with a little motivation why we need this survey. What is specific about medical imaging? Medical imaging provides us with a very popular application of visualization. There are many papers, especially in SciVis, that use medical image data as a proof of their concept. Medical imaging provides unique and very complicated data. In general, medical data is very messy. There are no specific standards. Patients can look very different, and it's really hard to understand the complexity that is captured in medical imaging data. And it is affected by uncertainty in various manners. And we will come to that point later, what various manners means. I brought a little example, which is an MRI of a patient's head. And in this head, you can see the patient's brain. And in this brain, there is a tumor located. And from the image, it is really hard to determine what part of the brain is tumorous. So for the visualization approaches that exist, we can ask ourselves, which uncertainty-aware visualization approaches exist that fit medical imaging? So now we come to the content of this talk, and we will first talk about what medical imaging actually is, which is probably not known by everyone. And then we will define uncertainty and define the types of uncertainty that exist in medical imaging. Resulting from that, we will come up with some requirements of uncertainty-aware visualization in medical imaging. Followed by that, I will show you our paper selection criteria, which we defined to determine which papers will be included in the state-of-the-art analysis. Followed by that, we will start with the actual state-of-the-art analysis, and we will show you how to create a medical imaging pipeline based off the conducted state-of-the-art analysis. And this will conclude by open problems that we determined based on our state-of-the-art analysis. So let's start with the definition of medical imaging. Medical imaging is concerned with the analysis, visualization, and exploration of medical images. And what this means in practice is there's usually a clinician that uses medical imaging in different applications. Medical imaging itself separates into three major categories, which is acquisition, which means the generation of medical images, the transformation, which is the analysis and processing of images, and the visualization part, which is finding representation that is visual of medical imaging. Applications can be broadly separated into four categories, and those are diagnosis, treatment planning, intraoperative support, and education. So let's have a closer look at medical imaging and their subcategories. I already told you that there's acquisition, transformation, and visualization, but that's not everything. Those categories further separate. For example, acquisition can be done for computer tomography, position emission tomography, ultrasound, and many other acquisition techniques. The transformation part can also be separated into three major subgroups, which means pre-processing, including image operation and image registration, segmentation, and feature extraction, which further separates into geometry extraction and tractography extraction. For the visualization part of medical imaging, we can build up three major categories, which are glyph-based visualization, indirect volume rendering, and direct volume rendering. So how does uncertainty come into play when we're talking about medical imaging? And before we can answer this question, we first need to define uncertainty. So assume you're measuring something, which is the C here, and you have actually a ground truth, which is C star, that you can compare to what you actually measured. And the difference between those things is actually an error. So an error requires a ground truth where you can say, I measured something and it differs from what I should have actually measured, and this is my error. For uncertainty, this doesn't count because uncertainty is not really defined in a standardized manner. So you have to somehow define how safe is what I measured. So uncertainty actually means the doubt of a measurement. And this doubt can be expressed and made in a lot of ways, but we will cope with two ways here. One is a bounded uncertainty, which means you define an interval around what you measured and say everything that's inside this interval is certain. Or what you can also do is you can use a probability distribution function, which tells you that what you measured is probably true, and the further you go away from this measurement, the less probable it will become. What can we also define on uncertainty? Uncertainty can be described, but you cannot really determine a fixed definition. So you can describe it by different categories. First one is the type. And here we can separate uncertainty into two major groups, which is aleaphoric. And this means uncertainty that is arising from the data. So everything that you measure varies, what we saw on the first image. And on the other hand, there's epistemic uncertainty, which is uncertainty that is arising from the computational model that you're using. A model is never perfect. You somehow approximate things that you see in physics and try to compute with them. And this is also introducing uncertainty. There's a dimensionality of an uncertainty event, which means that uncertainty can come in different dimensions. It can be one-dimensional or multidimensional. There's a category where you say uncertainty can be numerical, spatial, binary, and there's a description which can be discrete or continuous. So now that we know how we can define uncertainty, we can also define different types of uncertainties in medical imaging. And this table can be found in our paper, where we sorted all sources of uncertainty and described their type, dimensional event, category, and description of the event. We also applied a color coding that shows what type of uncertainty accounts to what type of image processing approach in the medical imaging pipeline. For example, the first three types of uncertainties are accounted to the data acquisition process in medical imaging, and it contains positional uncertainty, pixel, voxel value uncertainty, and incompleteness of data. Positional uncertainty can mean that the image is misplaced in space. Pixel and voxel value uncertainty means that the value of the voxel can be wrong. Incompleteness of data means that there might be data that you actually would like to have, but it wasn't acquired. For the next category, the image transformation, there can be model inaccuracy, which means that the model is not perfect. There can be model incompleteness, which means that the model just doesn't know anything about the physical world we're in. And there is parameter boundary condition uncertainty, which usually refers to if you're using an algorithm, you often need boundary conditions, and selecting those boundary conditions can also be affected by uncertainty. The last category is about visualization, and it contains rasterization uncertainty, which happens when you map your visual variables onto your screen. Perceptual and cognitive uncertainty, which refers to the user that can have problems in understanding the visualization or can have cognitive uncertainty while understanding the visualization, and a decision-making bias, which means that you actually see something and you see how you should make a decision, but you're biased in such a way that you don't want to accomplish this decision. And the goal of all the visualization approaches that we target in the STAR is that they capture at least one of these uncertainties in a visualization. So now that we understand what types of uncertainty can occur in medical imaging, we need to define some requirements that need to be fulfilled to be a very good uncertainty-aware visualization in medical imaging. And how could we come up with those requirements? Because there's actually no literature on requirements of uncertainty-aware visualization in medical imaging. We discussed this with our collaborators and presented them a list of known requirements for visualization in applications. And those requirements were rated by our experts, and we used the most important requirements they selected and reduced them to high-level requirements. And those requirements are shown below, and they are, in fact, show the original data set. This is something that is very important for medical researchers, as they always want to see what was actually captured in a medical data set. The second one is show the related uncertainty to the original data set, which perfectly makes sense because this is what we're targeting here. And the third one is keep the cognitive load minimal. There is something that we can call the curse of uncertainty. And this means that it's often required to have a look at uncertainty of data, but you also add another dimension of complexity to this data. And therefore, the visualization needs to keep the cognitive load minimal, although it shows the data set and the related uncertainty. Before we can finally come to the part where we can actually present our state-of-the-art analysis, we need to tell you a bit more about the paper selection criteria. First of all, we use different search platforms to gather all the papers that we considered for the STAR. And those include IEEE transactions on visualization and computer graphics, IEEE transactions on medical imaging, computers and graphics, the EuroGraphics Digital Library, Computer Graphics Forum, uncertainty quantification in scientific computing, and we also extended the papers that we found here by Google Scholar searches and Springer link searches. What are we actually searching for? We composed keywords that we searched in all of the showed journals by having two parts. The first part goes along with uncertainty-aware visualization, uncertainty analysis, sensitivity analysis, ambiguity analysis, variability, and variation. We included ambiguity, variability, and variation to make sure that we capture the different types of words that can be used to announce uncertainty in a paper. The second part is actually the part that includes the medical imaging pipeline. And in this part, we're actually using the words medical imaging subcategories, as I showed you some slides before, diagnostic, interoperative support, treatment planning, and education. So this means the first part actually defines that we're looking somehow in the direction of uncertainty visualization, and the second part shows that we're interested in medical imaging or any of their subcategories and any of the applications that we're targeting in the STAR. And by using all those keywords in all the search platforms, we came up with around 250 papers, and we also had a criteria of inclusion in the STAR, which was first, the paper has at least one example from medical imaging. As I said before, science papers often use medical imaging as a proof of their concept, or the STAR, and the STAR needs to contain uncertainty visualization approaches in general. So now that we defined the requirements of uncertainty-aware visualization in medical imaging, and we determined the selection criteria, we can come to the point where we can actually conduct the state-of-the-art analysis. And before we can do that, I want to show you how we structured our analysis. We used the medical imaging pipeline and all the subcategories that we saw before to make an intuitive sectioning possible. There's also a dedicated chapter on applications of medical imaging, as they usually consider multiple steps of the medical imaging pipeline. Our state-of-the-art analysis starts with the acquisition process, and in this chapter we included all uncertainty-aware approaches that target ultrasound, computed tomography, magnetic resonance tomography, diffusion tensor imaging, and positron emission imaging. There are further imaging techniques available, but they are not as popular as the selected ones. This is strengthened by the paper we found that highlights the selected modalities are the most important for medical imaging. For example, we found an uncertainty-aware visualization for ultrasound by Berg et al., who used a brown overlay to indicate uncertain areas in the image. On the other hand, Stevens et al. Used time uncertainty to indicate which time steps are more certain than others by providing a color coding. Here, light yellow areas indicate high uncertainty. When considering diffusion tensor imaging, which is shown on the lower images, we found an approach by Alida et al. That captures the uncertainty in eigenvalues using bootstrapping. This is visually indicated by a color coding. On the other hand, Markov chain models are also a popular tool to measure uncertainty in diffusion tensor imaging. Behrens et al. Used the color coding to indicate this resulting uncertainty with a rainbow color map. In our state-of-the-art report, we provide different tables, one for each major category of medical imaging and one for applications that indicate which found approaches are capable of fulfilling the defined requirements. For the acquisition step, which you can see here, we found that the ultrasound and the computed tomography were the only approaches where we can find an approach that fulfill all requirements. Unfortunately, for the categories magnetic resonance imaging, diffusion tensor imaging, and positron emission imaging, we were not able to find an approach that tackles all the requirements. The next category is the transformation step of the medical imaging pipeline. This step further separates into pre-processing. In this category, we can make subcategories for image operations and image registration approaches. Gillmann et al. Provided a visual approach that allows to apply arbitrary image operations. The system helps in following the development of uncertainty throughout the application of the different image operations. For image registration approaches, Van Gogh et al. Used the Bayesian neural network to compute the registration transformation of two images. Here a heat map is shown that indicates what are the uncertain areas in the mapping. Rison et al. On the other hand, used Boltzmann distributions that show variability in the mapping process using a color coding. To summarize this category, we observe the respective table. Here we see that the solely one approach for image operations is completely uncertainty aware according to the defined requirements. On the other hand, image registration approaches provide multiple approaches that fulfill these requirements. Let's continue with the next step of the transformation, which is image segmentation. Image segmentation is a fundamental task in medical imaging as it is involved in nearly any task of medical imaging itself. This comes down to the necessity of separating different tissues or structures in the human body for further analysis. The first observation we can make is that machine learning is massively on the rise. I want to show you 5 examples that we extracted from our state-of-the-art analysis that show the variety of the found approaches. Altai et al. Provided a visualization that indicates the uncertainty of the performed segmentation using different color codings. The second approach is provided by Passini et al., who used volume rendering with different opacities to indicate uncertain areas. The third approach was presented by Batra et al., who used lines to indicate different segmentation results that can occur when using different boundary conditions for the segmentation process. Saur et al. Used Bayesian decision theory in the fourth example to output a probabilistic segmentation result that can be visually encoded using a grayscale. At last, Gillmann et al. Presented a visual guided segmentation approach that shows certain areas of a segment in bold colors and uncertain areas with a high transparency. To summarize this, we determined a variety of uncertainty-aware segmentation approaches in medical imaging. Unfortunately, solely around a third are able to fulfill all the requirements we defined in our state-of-the-art analysis. Here we identified that the increasing use of machine learning, especially using Bayesian decision theory, may improve the statistics in the upcoming years. Considering the last step in the image transformation area, we examined feature extraction approaches. Here we can make a separation between geometry extraction approaches and tractographies. The left example shows an adapted Martin cubes approach presented by Zhang et al. That aims to adapt the surface according to uncertainty information contained on the original image. On the right side, we can observe an approach by Glancing et al. That use color coding on the extracted tractographies to indicate the uncertainty contained in the lines. To summarize this, we can see that we were not able to find an approach for surface extraction that is able to fill all requirements that we defined. On the other hand, all found approaches for tractography extraction under uncertainty are able to handle all three requirements that we set up for this analysis, which is a very positive result. Now that we discussed all categories contained in the medical image transformation step, we can move forward to the visualization step. Here we found three subcategories, which are direct volume rendering, indirect volume rendering, and glyph visualization approaches. In general, we can observe that these approaches often lack the ability to relate to the original dataset. But first, some examples. The first example shows a volume rendering by Nis et al., who uses two-dimensional transfer functions to provide uncertainty-aware visualizations of human structures. This is an outstanding approach as it covers a variety of uncertainty events and contains an extensive evaluation of the provided visualization approach. The second approach was proposed by Trapezkowski et al. That used color coding on the rendered geometry to indicate its uncertainty. At last, Gerik et al. Provided a glyph-based approach that aims to cover the potential variation in a visualized tensor by a surrounding surface. As a summary for the found visualization approach, we found two approaches of direct volume rendering that are able to deal with the made requirements. Unfortunately, indirect volume rendering and glyph-based volume rendering approaches could not have been found such that they fulfill all requirements. This is probably due to the visualization approach itself that is not related to the original data. To this point, we discussed all approaches that deal with a single step in the medical imaging pipeline. As already mentioned, we aim to highlight approaches that target a specific application as well. Here we separate the found approaches into four major applications that are diagnosis, treatment planning, intraoperative support, and education. These approaches often make use of visual analytics approaches, are highly interactive, and use multimodal data input. The first example is presented by Christofer et al., who provided a dashboard for the visualization of stenosis in arteries. Here, uncertainty of the blockage is indicated. Second, Brecheisen et al. Provided a visual analytics tool that aims to help users examining tractographies and their uncertainty. Third, Wiese et al. Provided a radiation therapy planning system that visually indicates radiated tissue and shows the probability of surrounding tissues to be affected by the radiation. The fourth example by Barra shows a surgery assistance tool that helps indicating positional displacement of the surgery tools in the patient's body. And at last, Emutes et al. Provided a Jülich brain atlas that is a standardized brain map based on multiple patients that separates the brain into different areas. Here, areas that are uncertain are highlighted in red. As a summary for applications of medical imaging that consider uncertainty information, we can see that we are not able to find any approach that is designed for education. This was a very surprising result. For the remaining categories, we found approaches that are able to fulfill all requirements, especially in the category of intraoperative support. So far, I summarized for you the found approaches of uncertainty-aware medical imaging. As we saw, the approaches that deal with applications provided a high potential as multiple steps of the medical imaging pipeline are used. In the presented star, we aim to show which parts of the medical imaging pipelines can be composed to create entire image processing pipelines as a future reference for the reader. In this figure, you can see all the different categories that we examined in the state-of-the-art analysis. So far, we consider these techniques by themselves. When we have a closer look at the image acquisition techniques, we can separate them into scalar fields and diffusion tensor imaging. Diffusion tensor imaging is often reduced into scalar fields as well. Starting from scalar fields, we can make use of image processing approaches, image segmentation, and surface extraction approaches. These results can then be visualized using direct or indirect volume rendering. Alternatively, diffusion tensor imaging can be visualized directly by any of the visualization techniques. On the other hand, diffusion tensor imaging can be used to create tractographies that can be visualized by indirect volume rendering or can directly be visualized by glyph-based approaches. So considering this table, you can see how you can compose entire medical image processing pipelines using the single steps that we provided in the state-of-the-art analysis. This brings us to the last point of our state-of-the-art analysis, the open problems that we identified throughout our work. The first open problem is the identification of proper uncertainty quantification approach. There are usually multiple approaches available, and the question is which one to use. The next problem is the uncertainty in clinical studies. When using medical images for clinical studies, the question arises, how does this uncertainty affect the outcome of a study? The third problem is a lack of exploration tools for uncertainty in medical image data. Clinicians need to be enabled in understanding the made uncertainty quantifications and therefore require tools to explore them. Further knowledge from other applications, such as environmental sciences that also deal with massive uncertainty, needs to be taken into account to see if we can learn from this. The teaching of uncertainty-aware medical image principles is also an open problem, as medical students should learn about them to create an awareness. Next, the connection to sensitivity and ensemble visualization needs to be further examined. The disciplines provide a lot of techniques that might be useful in uncertainty analysis. Next, we want to promote more usage of machine learning, and as usual when dealing with machine learning, we also need mechanisms to understand their decision-making process, to create trust in them. As we showed, visual analytics approaches seem to promote an implementation of uncertainty-aware principles, so an open problem is how to incorporate them in a more systematic manner in medical imaging. And at last, there does not exist a ready-to-use framework that assists users in exploring existing uncertainty-aware techniques in medical imaging. And with that being said, I would like to come up with a quote from William Osler, who is actually one of the founders of modern medicine, and he once said, "Medicine is a science of uncertainty and an art of probability." I would like to thank everyone for your attention, and I'm open for your questions.
Yeah, thanks a lot, Christina, for this very structured, systematic approach and also this comprehensive overview of uncertainty-aware visualizations in medicine. I look in the chat and see questions from Nuska Smith, University of Bergen. Nuska is an expert for medical visualization, so that's not surprising. Thanks for this comprehensive survey. Maybe a provocative question. How often have you encountered that a clinician or medical researcher asks for uncertainty visualization without us, visualization researchers, proposing it?
That's a very excellent question, Meinecke. It's a different term they're using. It's not like they're saying, I want to have something that visualizes the uncertainty in my data, because they don't really think about it in the way that I presented in the start. Mm-hmm. They're more like, okay, I have this data and I'm by myself not really sure what I can see in that data. So is there any way that you can help me? And every time you talk about something specific, like, okay, now we try to classify this and that disease, and then you try to get some information for them on like what classes do we actually have. And then you come to the point where they are like, okay, it's actually not super precise defined classes. It's more like it can also be half this, half that. And then you encounter, okay, there's always this problem of uncertainty. They just don't phrase it like that.
Mm. Yeah, that is probably correct. That fits also to my own experiences. Something they are very well aware of are all the artifacts and noise in medical image data. Yeah, so my wife is a radiologist. She has whole textbooks on artifacts in CT data, another one on artifacts in MRI data, and the third one on artifacts in ultrasound data. Yeah, so everything that could be misleading directly in the image data, that is where they are really familiar with and already educated very, very well. Yeah, but that does not apply to derived visualizations. Yeah, heavily post-processed visualizations, as they would call it. Nuska has a follow-up question. In which specific applications do you think uncertainty visualization is most crucial or has the most potential for impact to clinical practice?
I think the best thing we can do with uncertainty visualization for clinicians is that we can make them aware that their own classifications on diseases and on treatment, on how to plan things, underlies a lot of uncertainty and needs to be captured. And I think that holds for a lot that goes with diagnosis. I think that's the first thing where every time you go to a doctor, if it's not only a cough or something, then they're also like, okay, this might be this and that, and I'm pretty sure about that. But a clinician would never say, okay, this is definitely this and that, and you will die in 3 days or whatever. So that's, I think that's where we can start making the best contributions with this topic.
Mm-hmm. For diagnosis, I would say, again, they know a lot about differential diagnosis. If you go to a physician and at the end you get a head MRI, a brain MRI, then they know this looks like multiple sclerosis, but could also be another type of inflammation or even a brain tumor. And then they have really decision trees, algorithms that tell them, we have to make this or that investigation to further discriminate the options. So in particular, with respect to diagnosis, I would say they are quite aware of this. One specific diagnostic example where I really think that 3D visualizations carry an uncertainty that should be conveyed is vessel visualizations generated either with volume rendering, with a transfer function, or with isosurface rendering with a threshold. And that is where they really read in their textbooks, you should not rely on one visualization. You should change the parameters a bit, the transfer function or the ISO value in order to see different variants. And only if there is always a stenosis, then there is a stenosis, and otherwise it was misleading. So there I really would agree. Christina, maybe I can have a follow-up question to Nuska's question. I think that medical researchers and clinical practitioners need to be discriminated. They are quite different. That's similarly different, like a conventional computer scientist and a computer science researcher aiming with everything he is doing on a scientific publication that is highly important. That's completely different from doing software engineering in a company. Yeah, and I think the difference between a clinical practitioner and a medical researcher who wants to make his scientific contribution is as large as this. And that must have consequences also for requirements and for the suitability of uncertainty analysis and visualization. What do you think about this?
I mean, you're totally right about that. I think what is missing for them, and that comes a bit down to what you say, that they are very different. They're lacking a bit a systematic way of treating data, of treating their knowledge that they have and the information that they have. And I think that is something that I would really like to contribute to them, because I feel like this is going to be a helping point, not only for uncertainty visualization or uncertainty analysis in general. I think that is something that could contribute into that entire science in general. And it's really hard to get together with them sometimes, because when I was a child, I always thought medicine is like science as I imagined it, as a computer science to be science working. And now I figured out that they are very practical. They need to get stuff done. They need to help people, and it's a question of time and a question of resources, and they have to deal with a lot of problems. So we need to find a way to bring our system to them without making them feel like, okay, now there's all these things coming up and I don't understand what they want from me. And I think that's the biggest challenge, whatever you're trying to work with clinicians.
Yeah. Maybe one more related question. Uncertainty visualization requires that the uncertainty is quantified first. Yeah, and when it is quantified and characterized, you can visualize it. Do you have the impression that the uncertainty quantification is in most cases good enough, or is this also an area for further research?
It is absolutely an area for further research, because depending on what uncertainty you're trying to measure, there exists more or less well-working measures to handle that. I mean, it's not that you have something where you can compare like with an error. You do not have the possibility to see how good your measure is. So it's always a bit of guessing and like hinting on, okay, this might be a data point that doesn't really show what it's actually supposed to show.
Yeah.
And what I would really like is some points, that let's say ultrasound and computer tomography, that you have a lot of techniques that actually work really well for uncertainty quantification. But then the question arises, which one do you use, and which one is actually the one that you're interested in right now? And then you have to figure out what do you want, and then clinicians need to play around with that, and there is actually nothing where they can do that. I mean, they can come to me and say, okay, I have a feeling that I should quantify the uncertainty in this and that way, and then I'm going to do that for them. But there is nothing that helps them in just exploring that a little bit, and then figuring out by themselves what they actually want and what they actually need and what works best for them.
Yeah. Okay, thanks. Nuskite has another question. A couple of years ago, we have written a survey on multimodal medical data visualization and noted uncertainty visualization as one of the challenges. Has much progress on this topic been made recently, in your opinion? Uncertainty with respect to multimodal data?
So regarding the STAR, which I actually really liked, I wouldn't say there's too much progress being made. So I think the techniques that we reference in the STAR are pretty much the same techniques that have been on the Eurostar. I cannot remember that by heart, but it should be one or two new approaches that have been made. I mean, it isn't easy, especially the registration problem is a big problem, and will be becoming more big because we will have more data in medicine and more things that need to be registered. And that's so I would say, okay, there is slightly more progress in this area, but there needs to be done a lot more.
Do you have any specific ideas of what could be done? So far, I thought for registration, for example, there are typically grid-based approaches, and then what you can derive is how the grid has changed. So some cells get smaller, others get larger, and others distorted. And then, of course, that gives you something that you can analyze and quantify the locally different registration error. But maybe there is nothing much better than this.
So I would say that's kind of like a logical way to go. And I think that's also something that gives you a lot of information so far. What I think what comes into play there too is if you have this multiple data sets and then you want to see how do they overlay now, and the visualization component of the registration process, I think, is even more dramatic than the uncertainty, like figuring out the uncertainty of the registration process itself. I think that's, we can say, okay, in this and that area, the registration process might have failed, or it's probably not that what you wanted. And I think that's, it is a problem. I don't want to rate down my own topic, but I think in talking about multimodal analysis of images, the visualization part and the analysis part is definitely the bigger problem right now.
Okay, yeah, thanks again. Nuska seems to have no further questions. Yeah, and even my important questions are also done. So yeah, I ask once more the technician whether there is something from the chat that I should consider. If this is not the case, even if we are a bit early, I think that's not a problem. Everyone enjoys a lunch break. Then I would like to close the session. Thank you again, Christina, for this nice and insightful talk, and also for handling all our questions. And also thanks again the authors of the first STAR and the audience for asking questions and making this a lively event. Yeah, thanks a lot. Bye-bye.